Swayam Prabha. Digital India. Educated India.
Hello. Today we will start a new topic, sizes of sets. In particular, we will look at countable and uncountable sets. Okay, so what does it really mean? We will make the definitions mathematically precise later, but intuitively let me give you an idea. If S is a set or A is a set, if it is finite, then I can definitely talk about the size of A, the number of elements in it. And if it is finite set, I write it as size of A is less than infinity. Now, problems come when we deal with infinite sets. Okay. Now, just writing the size of A equal to infinity does not make things clear. Okay, not clear. Okay, why? We'll eventually come to the conclusion that this notation as such makes little sense. Okay, so finite sets can be counted. Okay, so elements for example, if A is a finite set containing n elements, I can count them. This is the first element, second element, third element, fourth element up to nth element. And this counting process stops after all the elements of A are exhausted. Now, we talk about infinite sets. We can also count elements like this. For example, let's say this set is going to be very important in this connection. Set of natural numbers 1, 2, 3, 4 and so on. So naturally I can call this the first element, this the second element, this the third element, this the fourth element and so on. However large a positive integer is, this is a counting process, and then if I consider, let's say maybe write it this way. This is n and so on. Okay. So I can count elements of n as first element, second element, third element, fourth element, nth element and so on. This counting process does not stop. Okay. So, but all the elements of n are eventually counted. Right. So, this is an infinite counting process. But whatever integer n, positive integer n you give me, in the nth step of the counting process, that element is counted. Okay. There are many such sets where all the elements can be exhaustively counted. More importantly, there are also sets where no matter how you count the elements, you can never exhaust the entire set. Okay, so that is an important thing. There exist sets such that any infinite counting process fails to exhaust all the elements. So this is the basic, I would say, topic dealt with in this section. But this is very intuitive introduction to countability and uncountability. Let me make the notions precise, mathematically precise. Okay, so let us say A and B are two sets. We say size of A is less than or equal to the size of B if there exists an injective map F, let us call it F, from A to B. So, this is our definition. If there is an injective map from A to B, I will say that the size of A is no bigger than the size of B. That is quite a natural thing to say because this F produces an embedding of A in B. Okay. Therefore, B cannot be smaller than A. Okay. Now, let us see some examples. If A is a subset of B, then consider the canonical inclusion map iota, taking A to A. This is definitely an injective map. Okay. This is the canonical inclusion map. Is injective. And therefore we can say A less than or equal to B in terms of size. In particular, this implies that because natural numbers are part of integers, set of all integers, so this is fine. Likewise, I can say set of integers less than or equal to set of rational numbers. This in turn is less than or equal to the set of real numbers, and so on. These are some special cases. Something like also you can think about n odd set of all odd integers, size of that less than or equal to size of all natural numbers, and so on. Let us now see something little bit non-obvious. I show that the converse of this is also true. Okay. So from Z, I have to define a map to the set of natural numbers. But that is not so difficult. So let's say 0 maps to 1, 1 maps to 2, minus 1 maps to 3, 2 maps to 4, minus 2 maps to 5, and so on. Okay, you can see the general pattern. What is the general pattern? N maps to 2n and minus n maps to 2n plus 1. Okay, for all n greater than equal to 1. Okay. So definitely this is an injective map because different elements go to different elements. 1, 2, 3, 4, 5 and so on. And therefore, by definition, the size of Z is less than equal to the size of natural numbers. This is also a bijective map. I can also think about a non-bijective map this way. For example, 0 goes to 1, 1 goes to 3, 2 goes to, minus 1 let me handle first. Minus 1 goes to 5, 2 goes to 7, minus 2 goes to 9, and so on. So this is yet another injective map, but this is not subjective. So this is bijective, whereas this map, although injective, is not a bijection. But that doesn't matter. Okay. So I can say this and this. Now whenever I have this two-way implication, I can say that these two sets are of the same size. Okay, to be more precise, definition, we say for two sets A and B, the size of A is equal to the size of B if size of A is less than equal to size of B and size of B is less than equal to size of A. That is equivalently if there exist injective maps some F from A to B and G from B to A. Okay. So example we have already seen. Size of n natural numbers is equal to the size of all integers. Okay. Okay. So this is our definition, the existence of injective maps from the first set to the second and another injective map from the second set to the first set. In that case, we will say A equal to B. And there is an important theorem which I will not prove in this context. So it is called the Cantor-Schroeder Bernstein theorem. This says that two sets A and B are of equal size if and only if there exists a bijective map H from A to B. Okay, so one side, if there exists a bijective map H from A to B, then that H is injective. H inverse is a map from B to A that is also injective. So, by our definition, these two sets are equal. The converse of the proof, that is the only if part, where we start with two maps F from A to B and G from B to A, both injective. Construction of a map, which is a bijection from A to B, is somewhat not straightforward, and I just want to omit the proof for this moment because this construction is very non-trivial. Okay, it can be done, but it is very non-trivial theorem. But we will henceforth use this theorem quite, I would say, frequently. Okay, so that's basically the important thing: size of a set, comparing size of a set, and equating the size of two sets. Okay, and this is often, if A is B, we often say, okay, this is just a term, A equal to B in size, then we say A and B are equinumerous. Okay, this is just a term. Now, with this insight, let us define countable sets. Okay, before doing that, let me prove a theorem. Let A be any infinite set then set of natural numbers, the size of that is less than or equal to size of A. Okay, so why? Okay, so I have to construct a function injective from N to A. Okay. Okay, so I pick an arbitrary element A1 in A and define F1 equal to A1. Then suppose that I have I have defined Fi equal to Ai, or let's say I equal to 1, 2, 3 up to n. And these are distinct. Okay. Now given that the set A is infinite, I can choose an AI plus 1 which is different from A1, A2 up to AN. Okay, I can choose some AN plus 1 which is different from A1, A2 up to AN. Okay, so A is infinite. So we never run out of elements, so we can choose AN plus 1 from A. Different from all of is A1, A2 up to AN. And then define Fn plus 1 equal to AN plus 1. Okay. So by induction, therefore, we have an injective map F from N to A. Okay. The rest follows from induction. Good. So this theorem says that I can embed the set of natural numbers 1, 2, 3, 4 and so on in any infinite set. This essentially implies that the size of this natural number, set of natural numbers, is the smallest possible infinity that we can have. Okay. Because in any other infinite set, n can be embedded. Okay. So the corollary of this theorem is size of the natural numbers is the smallest infinity. Good. Now, we actually denote this as Aleph naught. So this is Aleph naught. Okay. This is the symbol. If I am not mistaken, this is the Hebrew symbol. Aleph naught. Naught is definitely 0 here. Okay. So then I define countability. A set A is called countable if either A is finite or the size of A is same as the size of natural numbers, which is Aleph naught. Okay. This is the definition. Now, what does this mean? A equal to n. Definitely you have seen. Okay. So A is countable and let's say infinite. If and only if there exists an injective map F from A to N, because the other injective map from N to A, which we have seen in the earlier theorem, N to A, that is always there. Therefore, it suffices to have an injective map from here to here. And by the Cantor-Schroeder-Bernstein theorem, this is also equivalent to there exists a bijective map H from A to N or N to A, whatever is. Okay. So this is by Cantor, Schroeder, Bernstein theorem. Now this map essentially is or maybe I write it this way. I will have to make it. Definitely this is same. But I write it just opposite way. N to A. Okay. So how does it, what does it mean exactly? Having a bijective map from the set of natural number to the set of all elements A. This essentially means that A is nothing but H1, H2, H3 and so on. So this essentially implies the infinite counting process. Okay, so H1 is some element of A, H2 is another element of A, H3 is another element of A, and so on. And since this is a bijective map, the image of this map will be the entire set A. Right? Therefore, if I keep on counting using the function H, I will be able to exhaust all the elements of A, H1, H2, H3, H4. Okay. So whatever A is, whatever an element this is, small a is, it will eventually end up somewhere here. And it will be H of n for some n. Okay. So this is the infinite counting process, which exhausts all the elements of A. Okay. So this is the reason these sets are called countable. Definitely finite sets can be counted. The elements of finite set can be counted, and that is a case of finite counting process. But now we have an infinite counting process that never stops, but it eventually covers, exhausts all the elements of A. Okay. So, having proved this, okay, let me tell a few theorems. Okay, some theorems. Okay, 5 theorems here. Okay. Any subset of a countable set is countable. So proof fairly straightforward. Let A be a subset of a countable set B, so B countable. If A is finite, we are done. Otherwise, if A is infinite, B is also infinite, but then we have the canonical inclusion map, iota, from A to B. This is the inclusion map. Which is injective. Therefore, I can say the size of A less than equal to size of B, Okay, which is basically equal to the size of n, because if A is infinite, B has to be infinite, and since this is countable, it has to be the same size of this. On the other hand, we have seen that n can be embedded in any infinite set. Okay, so combining these two together, we can conclude size of A is equal to size of n. That is, A is once again countable. Good. Second theorem. This is somewhat little bit non-trivial. The union of two countable sets A and B is again countable. Okay. Why? This is the reason. So, A is countable, therefore I can write A as A1, A2, A3, A4 and so on, which may be a finite listing or an infinite listing, but this way, this is the first element, second element, third element, fourth element, this way I can write A. Likewise, B can be written as B1, B2, B3, B4 and so on. If that is the case, what about A union B? I can list the elements of A union B as A1, B1, A2, B2, A3, B3, A4, B4 and so on. And this way I can exhaust all the elements of A and B. Definitely there is a small catch here. Here I have assumed that A intersection B is empty, but that need not be the case if A intersection B is not empty, that is, if A and B are not disjoint, then some elements are repeated. Maybe A1 is equal to B2, so A1, B2 is once again listed. So I would just say then do not list the second appearance or occurrence of elements that are common to A and B. Okay. Then, so you have a sub list of this, maybe A1, B1, A2, A3, B3, B4 and so on, but that is still a complete counting of all the elements of A union B. And therefore, the union of two countable sets is again countable. Okay. In particular, I can extend this to any finite number of countable sets. Let k be a positive integer and A1, A2, AK countable sets. Then the union of I running from 1 to k, is countable. Okay, so proof is pretty straightforward. Induction. on k equal to 1, then A1 is countable. The union is also A1. So this is obvious. So now suppose that k greater than equal to 1 and the union I equal to 1 to k is countable. So this is the induction hypothesis. But then the union of I running from 1 to k plus 1, I may call this set B. Okay, this is nothing but B union I plus 1. But B is countable, I plus 1 is countable. Okay, sorry, I made a mistake. This should be K. This should be K. This should be K. K plus 1. This is countable. This is countable. Therefore, using the previous theorem, this union is also countable. Okay. Now use previous theorem. So this in particular establishes that any finite union of countable sets is again countable. Then the next result, I will prove something more complicated. This is the most non-trivial result of today. The union of countably many countable sets is again countable. Okay. So if this countably many implies finite, then we have already covered this. That's right. Okay. So we assume that n in n a collection of countable sets. Okay. Because the finite case is already handled in the previous theorem. So now let's say countably infinite collection of sets. So I can write a n as a n1, a n2, a n3 and so on. In general, a n m. Okay. So how can I count two-dimensional? So there are actually how many elements are there? A, I, J, I, 1, 2, 3, blah, blah, blah. J is also running from 1, 2, 3. Okay, some of these sets may be finite, in which case there is an upper limit on J. Some may be infinite, so there is no upper limit on J. Okay. So how can I, therefore, I would say, exhaustively enumerate this two-dimensional array of elements? Okay. The technique is, the trick is this. I will show you a picture which essentially shows the trick. Yes. So here it is. So here 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 2, 1, 2, 2, 2, 3, 2, 4, 3, 5 and so on. 3, 1, 3, 2, 6, 2, 3, 4, 3, 5 and so on. Some of these lists may end after a finite number of finite space. Okay. But anyway, they need not also end. But now the counting process is something like this. A11, then go back here. A12, A21, then go back here. A13, A22, A31, go back. Go to the top. A14, A23, A32, A41, go back to the top. A15, A24, A33, A43, A51, go back. A16, and so on. A25, A34, right? So this way, I get an exhaustive enumeration of all the elements Aij, right? Okay, so this gives me an exhaustive enumeration of all the elements Aij. And once again, as in the earlier, in an earlier proof, if some elements appear in multiple sets, then future repetitions, okay. So don't include the same elements multiple times. If you have already listed, don't list it anymore. Okay. But anyway, this scheme basically says I can handle a two-dimensional array of this direction countable, this direction countable. I can still enumerate all the elements. Every element Aij will be eventually listed. Okay. Maybe it will take something like quadratic time. Okay. 1 plus 2 plus 3 plus 4 plus 5. So, you can work out maybe I plus 1 plus j step something. Okay. Where exactly this is included. Anyway, that's not an important issue very much. But the scheme says that even a two-dimensional array, infinite but countable in both directions, can be enumerated exhaustively. Okay. So this has this implication. Okay. So again, a corollary of this, A, B, countable, then their Cartesian product A cross B is again countable. Okay, the proof is pretty obvious. For all A in A, define BA to be a set of all tuples of the form A comma B, set of pairs such that B is in B. Okay, fix the first element. Then you see that for each A, BA is okay, the map B to BA that takes B to A comma B. This is a bijection for any fixed A. Therefore, the size of B and size of BA are same. In particular, each BA, okay, is countable. And finally note that A cross B is nothing but this countable union A in A, B A. Okay. So by the previous theorem, it's the countable union of countable sets, and therefore this is again countable. Okay. So now this implies the first counterintuitive thing. Once again, this is a corollary of the previous corollary. Q, set of rational numbers, is countable. Why? The reason is this: I can write Q as fractions of the form A by B such that A is in Z and B is in N. The denominator we always keep positive. This is positive, negative or 0. Okay, but then I can view Q as a subset of Z cross N. Okay, why it is not equal? Why it's subset? Because certain fractions are counted multiple times. For example, 1 by 2, 2 by 4, 4 by 8, 100 by 200. They all stand for half. Okay. So, if I add to this the restriction, GCD AB equal to 1. Okay. Then this is a proper definition of Q. Okay. A by B, A is in Z, B is in N, and GCD of AB equal to 1. But then, I know Z is countable, I know N is countable, so their product, Cartesian product, is again countable. So this is a countable set because Z and N are individually countable, and this is a subset of a countable set, and therefore this is countable. Okay. It's as simple as this. So, although it seems that Q contains roughly a square number of elements, okay, as this or this, but that can still be exhaustively enumerated. Okay. So, that's all. I would say. So, what does this things imply in terms of the Aleph knot notation? First of all, we have proved the union of two countable sets is once again countable. So that essentially means this plus this is equal to Aleph knot again. And we have also proved that this need not be union of only just two countable sets. For in K in N, the union of K countable sets is again countable. And by using this result, I can say Aleph knot star or times Aleph knot is equal to Aleph knot again. In fact, for any finite k, this construction can be generalized. Okay. Once again by induction on k. So that's quite important. So now therefore we can say, maybe I start from n odd, n even, n z odd, z even, z, and you may also include the set of all primes, because you know there are infinitely many primes. Set of primes this is, and even you can conclude set of q. This is all of these are equal to LF. So these are all countable sets. Okay. In the next lecture, I will show that we are not always dealing with countable sets. Okay. So in particular, we will show R, the set of real numbers, is not countable. Okay. So how to prove not countable? That's not a very easy job, because proving countability involves supplying some kind of injective or bijective map. But proving uncountability involves more complicated construction, because it's a negative result. Just producing a map will not do. Okay. Anyway, so this is our first lecture on countability. We will talk about uncountability in the second lecture, and in the third lecture we will see the implications of this set sizes in computer science. Okay, so see you.